Okay, so today we'll start where we left the last time, and actually I believe we started the recording, yes we did, and from last time we're going to go over only the last few or approximately 10 slides which we have from the first part that we have here in this package, but I just want you to remind what we covered in the previous sessions. So we were discussing about the arrays of antennas which are located along a specific axis, and they have subsequent distances and inherent phase differences, which the phase differences will be the beta, and the distance between the two subsequent antennas, they can be denoted as d or d divided by 2. These are traditionally the type of approximations we may obtain when we talk that we may receive actually. So the center of the system can be at a distance of r, and if we have a number of two or different antennas, we have r plus d over 2 cosine theta and r minus d over 2 cosine theta. This is how we can construct the, let's say, this is how we can add the field vectors. And then afterwards, if we add the field vectors which come up from these expressions, which is shown here in equation 6.1, we come up with two major factors. One is the element factor, which carries the magnitudes of the fields. The second one is the array factor, which covers most of the angular distribution. So we started with two components, and then we moved further with more components. But I just want you to remind you that always the array factor, which has also the angular distribution, it is described in this form, as shown here, kd cosine theta plus beta. So most of the time, we will have to construct. We'll have to look at this specific term, and we may want, for example, if you want to find the maximum distribution of the radiated power. So if we want a broadside antenna, that means that with respect to the z-axis here, we want a maximum angle, because broadside, this is what is mentioned. So the maximum power distribution, it is going to look like this, okay? And then we want a maximum value of these factors for a broadside antenna, okay, which will be something like this. And how do we spell broadside? This is how it is, okay, broadside. So if we want the maximum value here, that means that cosine should be maximum. That means that this factor is equal to 0, and this factor, it is equal to 0 if beta is equal to minus kd cosine theta, okay? And then in this case, what is, and again, if this is broadside, that means that the theta is equal to pi over 2, okay? So if this is equal to pi over 2, cosine pi over 2 will be equal to 0. That means that we may obtain a broadside antenna, which means that it will radiate most of the power along an angle of 90 degrees with respect to the z-axis. Then we don't need to have a phase difference, inherent phase difference between any two subsequent antenna components, but it can be simply equal to 0. Now, for this broadside antenna, if we want to determine the null, so if you want to determine the null, okay, then what we need to do is that we have to equal to 0 this whole term. And this whole term is going to be equal to 0 at whenever the cosine, as we can see here, whenever this cosine here, it is going to be equal to 0, which means that the angle is equal to 90 degrees or pi over 2. In that case, we just have to play with the numbers, and often we may have to carefully deal with this with the kd. D, it is most of the time described as a function of the wavelength. K, it is equal to 2 pi divided by lambda, okay? So this was what we covered mostly during the last time. We talked about the broadside antenna, we talked about the end fire antennas. So this was just about theory, then I might just jump toward the end pretty fast. So this was, let's see. So this was some antenna which was not, this is a scanning antenna, and scanning antenna, this means that we can point the radiation along a specific angle, theta 0. In this case, the theta 0 is going to be this angle, which is measured with respect to the z-axis, so that's the theta. And then apparently we have a theta which is around 60 degrees. If this is the case, cosine 60, it's equal to 1 over 2. And if this is equal to 1 over 2 times k, it is 2 pi divided by lambda. And now it remains on the respective value of d that we can select. Now the d, if you remember from last time, we can preserve the expected angular distribution if d it is smaller than lambda. So this should be something that we should remember. Okay. So if d is smaller than 1 wavelength, commonly we analyzed cases when d is equal to lambda over 4, or when d is equal to lambda over 2, and similar values. So here, if this is k, okay, this is k, cosine 60 is equal to 1 over 2, and d, this, it can, let's assign this one as lambda divided by 4. If this is lambda divided by 4, this cancels out. That means that the phase difference between two subsequent units can be this 2 divides like this. So this can be pi over 4. So this pi over 4 phase difference between subsequent antenna components, including a d which is equal to lambda divided by 4, will produce an angular distribution or scanning array antenna which will be equal to 60 degrees. Okay, so now, so these conditions drawn here, this will give this distribution. Of course, unfortunately, we get some minor lobes which are given here, and to find to see what so often an important component of the antenna is the voltage ratio between the major lobe and the minor lobe. So in this case, one can measure a voltage right here and measure also a voltage right here. The ratio, it will constitute the voltage ratio. And this ratio, it can be described as a dimensionless quantity and also in decibels. Now, what is essential for antennas when we try to design them, there are few components, but for the moment, at least regarding what we are talking so far, is that one essential aspect is the angle where we want to have the maximum power radiated, so that's one. And secondly, we may want to design an antenna that has a specific ratio of the minor lobes to the major lobes. Okay, so this ratio, it is an essential component which we need to analyze it a lot for the antennas. Then, last time we solved, we looked at some examples, and let's try. We may try to remind us once again. So we can have broadside antennas, we can have end-fire antennas, and here from this graph, what we can do is that we can determine what should be the length of the antenna in case we want, for example, if we want a broadside antenna which can have, let's say, subsequent, wait a second, it can have half power. So let's assume we want an antenna that has a half power beam width of around 2 degrees. That means that this is a very narrow distribution of the power. So let's go like this, and let's assume that we want the antenna to be pointing around, along a direction of 30 degrees. So then we have to follow this graph, and then to have an antenna which spreads out the radiation at an angle of 30 and has a beam width of 2 degrees, which is a very narrow distribution. That means that we have to look for an antenna which is equal to lambda plus d divided by lambda. This is equal to 50 wavelengths. Okay, so this means that this will be equal to 50. So this is 50 lambda. That means that depending on the d, we have to find the L. So for a moment, let's have this expression. So given these two values, which are shown here, 30-degree angular distribution, 2 degrees beam width, we get 50. Then if D, let's assume for a moment, if D is equal to lambda divided by 2, half of a wavelength, that means that L, it should be equal to what? L should be equal to 50 lambda minus 0.5 lambda, so this makes 49.5 lambda, okay? So this is going to be the length scale of the antenna, given the specific numbers we mentioned as we were explaining. And one thing that I can add here, when you see this slide, and I really want to see the slide number because, okay. I wish I had seen the slide number because, okay, anyway. So we need, what we see from here is that when we deal with antennas, the mathematical apparatus is pretty much relatively complex mathematical tools or apparatus. Now, let's go back to where we left the last week. And so last time we were talking about array factors for several antennas. And I believe that's where we left last time. So let's assume if we have an even number of antennas and an odd number of antennas, we are going to expect an array factor, which is going to look like this. If the distance between the antennas is equal to D, then this is what we observe. So these will be the antenna components above the zero, and these will be the antenna components below the zero. Since we observe a symmetry between this term, and similarly, like this one, and this one, that means that we can combine them together into several terms which are described as a function of cosine. Now, if we combine two terms into one, that means that we're going to have, for n antennas, that means for n antennas, we're going to have n divided by two terms, okay? So let's say if we have 20 antennas, so let's write this here. If we have 20 antennas which are composing into a large array, a linear array, until now, we are simply discussing linear arrays, which means that the antennas are put in line. Then for 20 antennas, that means that we're going to expect 10 different terms, okay? So n maximum is going to be equal to 10. So let's do this one. N maximum, this is going to be equal to 10. But what is tricky is trying to determine these ANs. What should be these A's which are provided here? To find the A's, we use several approaches. The first approach that we briefly mentioned last time, it was a binomial distribution. The second one is the Chebyshev distribution. And here, this has to do with very elegant polynomials, which is a Chebyshev polynomials, which is it has very nice harmonics. So all these arrays, they are done to find the excitation coefficients. And last time we said that the excitation coefficients can be described, or we can obtain those using symmetry, which is seen in this matrix. Now let me see. Okay, again. Now here we talked briefly last time. So for example, if we have two elements for an antenna, which is this, then that means that we have to determine only one element, only one A1, okay? So let's bring back to this discussion. So the number of n, it's always going to be half of the number of antenna elements. So if we come here, that means that two antenna elements, that means one coefficient. Three antenna coefficients, two antenna coefficients. So that means that we have to find A1, okay, and A2. So that's what we need to obtain. And now A1, at least for when n is equal to 3, we have A1 or maybe it's easier to look for the A2. A2, it's here, okay, but and here A1, we have 2A1 is going to be equal to 2. Okay, because whenever, so we should always expect a relationship like this. 2A1 is equal to the central terms, okay? Let me try to see if we can see this here. I think it was, yeah. So it is almost clear from here. So this 2A1, it will always appear there in such a way. 2A1 is equal to 2. That means that A1 will be equal to 1. Then for a moment, if we have 4 antenna elements, in these 4 antenna elements, A2, we have still 2 coefficients, A1 and A2. This is A2, sorry, this is, yeah, this is A2, and this is A1, okay? So, whenever the number is even, it is relatively easy, okay? Because, for example, when we say relatively easy, this will be A1, okay? This will be A2, this will be A3, this is A4, and this is A5, okay? Now, similarly, when n is equal to 9, we go, sorry, what have I done here? This is A1, A2, A3, this should be A4, I should have drawn it like this, and this is A5, that's good. But the issue is, whenever we have the odd numbers, A1 will always be half of this. So A1 is 35, here A1 is 10, here A1 is 3, okay? If A1 is 3, A2 is 4, A3 is 1, and similarly. Now, when n is equal to 6, we have 3 terms, and these 3 terms of the antennas, the excitation coefficients will be as follows. This is A1, this is A2, this is A3. Then we move here, A1 divide by 2, A2, A3, A4. Similarly, A1. So A1, we should always look in these 2 columns, okay? So A1, it's hidden here. This is the columns of A1. If we have an element at the center, we divide by 2, we get A1. If there is no element in the center, we read A1 straight from the respective numbers. That's good. Let's move ahead. So this is how we try to determine the coefficients for the binomial distribution. Now, these are again some examples. We can move faster here. So A1 is equal to 3. Here, A1 is 3. A2, it's 4. A3 is 1. That's good. And this binomial distribution, this is again what is, this is, I believe, yeah, this is the center. That means that if this is the center, we should strictly read the values. We don't have to divide the center element by 2, but that's what are going to be the excitation coefficients of the antenna. So these excitation coefficients are going to multiply the amplitude of the electric field. So yeah, now here we have normalized array factors. We can this design procedure. So here we have the design procedure of a specific antenna. But now at this stage, what we are talking about actually is we're talking about the determination of the AN factors or of the excitation factors. Now, at this stage, we are learning the binomial distribution of the coefficient factors. So that's what we are mostly taking care of for the moment. Now, once we determine what is the excitation coefficients for a specific antenna, we have to determine then what is the half power beam width and also the directivity. And these expressions, we can derive those, or we can take them, of course, directly from the textbook. That could be easier. And these are expressions that we can include in the cheat sheet. What I noticed is that chapter 6 did not have a cheat sheet or list of equations at the end of the chapter 6, probably because there are too many. Now here we see an example of how we can design the antenna. This is the directivity which is given by this expression. If we substitute here for the directivity, this is what we find as a function of the wavelength. So here we have an example. We're given a certain number of antenna components. It's going to be 10. The distance between the two components is going to be half the wavelength, and we need to use the expression for the half power beam width, which in this case it looks like it's going to be 20 degrees, measured in degrees, but this is the approximation that we use. The exact value is going to be something around 20.5. Then we can use this expression, which is given here for the directivity. It looks like that it's a really good approximation, and the best approximation, most probably, it's something like this. So this is going to be 1.77 times square root of 10 in this case, and yeah. So keep. So wait a second. I just want to keep all of these numbers. Okay, sorry. And now let's go to the second part of the class material, which has to do. Sorry. Okay. Now, so far, we discussed the calculation of the excitation terms using binomial distribution. Okay, so that's what we were dealing with. Now we're going to use a different type of approach, which is we're going to use the Chebyshev polynomials. That's the mathematical tool that is going to be used. But the array, if we use the Chebyshev polynomials, it will be called the Dolph-Chebyshev array. Wait a second, no. So Dolph-Chebyshev array is called whenever we use these types of polynomials, of which we're going to talk in detail how they look like. Now, the excitation, there are some approximations so that the Dolph-Chebyshev array coefficients, they can converge to the binomial distribution coefficients, and sorry. So actually, these coefficients that we do observe here, if they converge, let me say it this way, which they do, we might expect that when we find the Chebyshev polynomials, we might be expecting numbers that look like this. Okay, when you see like this, which is 100, little less than 100, half of 100, 10 to the power 1, 10 to the power 0. Okay, so this is how the numbers are expected to change. Okay, so let's come here. I thought we could observe. Yeah, here we are. Yes. Okay. Now again, we have to calculate the array factor of a specific antenna, and in fact, whenever the antenna it has an even or odd number of elements, then the symmetric amplitude excitation, it has been proven that this can be expressed as a summation of m or m plus 1 cosine terms. Okay, so we can have a lot of cosine terms, and if we add these, they're going to make a distribution as a function of angle theta. But this is going to be either an odd number of cosines or an even number of cosines. Now, the largest harmonic of the cosine terms is one less than the total number of elements in the array. So this means that if we have an antenna which can have 10 elements, if n is equal to 10, then the largest harmonic is going to be the 9th harmonic. And this 9th harmonic, what this corresponds to cosine u to the power 9, okay? So that's what it is. Of course, it looks like it's a very fast oscillating function, but this cosine to the power 9u, we're going to see that we can construct an equivalence with some polynomials which we call Chebyshev polynomials of 9th order in case the number of antenna components is 10. So that's the idea we're going to use. If the number of antenna components is 101, that means that the largest harmonic is cosine to the power 100, and then the array factor, it can be described as a function of the Chebyshev polynomial of degree 100. That's good. Each cosine term whose argument is an integer times a fundamental frequency can be rewritten as a series of cosine functions with the fundamental frequency as the argument. So what we observe here is that now the largest harmonic of cosine terms, so let's assume it like this. So now fundamental frequency, it is, let's say, so this will look something like this. This will be cosine, let's assume, omega 0 t. So let's assume this is the fundamental frequency, omega 0. But then the higher order terms, they will have cosine. Now the argument, it is going to be integer times the fundamental frequency. Now integer times, this means the following. We can have expressions like this: cosine 9 times the fundamental frequency, 9 omega 0 t. Okay, so this would mean, for example, a Chebyshev polynomial of order 9 is going to have the highest harmonic, which can be described like this. At the same time, we can use wonderful properties of cosine 9 omega t to express this one as a function of cosine omega 0 t alone. But this will have several terms, and we can see that how this can be expanded. So let's assume, for example, we want to describe this one as a function of cosine omega 0 t. That's good. This is what we are going to see in the future slides. So now these cosine functions, they can be expanded, as we said. So this is cosine mu. This can have a coefficient of 1. This is going to be cosine mu. This is going to be cosine u. But here there is a mistake here. The cosine 2u, in fact, this should be described cosine square u. Okay, don't read this as 2. So that's a mistake in these slides. At the same time, cosine 3u is equal to 4 times cosine to the power 3. So let me put it like this. So this 4, cosine 4u, cosine times 4 times the fundamental frequency. So the frequency terms we multiply by 4. This is going to be equal to 8 cosine to the power 4. Okay, and this is cosine to the power 5. This is cosine to the power 3, cosine to the power 2. So apologies for this mistake, but it should be okay. So this means that this cosine mu, this can be described as a vector which has coefficients of 8, minus 8, 1. And this 8 minus 8, 1, this is multiplied with cosine to the power 4 u and cosine to the power 2. So this is cosine to the power 4. This is cosine square term, and the last term, this is cosine to the power 0. Okay, so that's why we observe cosine to the power 0 is 1. And now similarly, cosine 5u, it goes on like this. This has coefficients of 16, minus 20, plus 5. And so on and so on. So what we tried to describe in the previous slide, it was that the highest frequency term, so cosine 9u, it can be described as 256 cosine u to the power 9. Okay, wipe this out. And cosine 576 cosine 7 to the power 7 times u. Now these coefficients, which we care a lot, this is what we said before in the previous, a few minutes ago. We said that these coefficients that we observe here are going to be comparable to the binomial distribution. But let's move ahead again here. So the cosine mu of the first order, when m is equal to 0, so cosine 0 is equal to 1. This is Chebyshev polynomial of 0th order. Okay, so Chebyshev polynomial of 0th order, this is what it looks like. And normally, what is interesting is that these Chebyshev polynomials, they have a very interesting property, which are amazing. which is the following. So let's assume for a moment, so how can we do this? Let's think for a moment, what is this? This says cosine inverse z something. Now, if this is talking about cosine inverse, what does it mean? So it looks like this is looking for the angle, okay? So this means that alpha, because alpha is an angle, will be equal to cosine inverse z, okay? Then if we take the cosine of both sides of the equation, we can obtain that cosine alpha is equal to what? Is equal to z, because cosine of the cosine inverse, the inverse functions, we simply get z, okay? So for a moment, so let's remember that we can extract this formulation from this expression, okay? So this expression that we see here, we can write it like this: cosine alpha is equal to z. That's good. Then let's assign what happens for m equal to 0. Imagine for a moment you set m equal to 0. If m is 0, what do we observe here? So here we observe that the 0th order polynomial will be equal to the cosine 0, which means that this will be equal to 1. Okay, this is when m is 0. Then, so when m is 0, we get the polynomial is equal to 1. That's good. When m is equal to 1, let's see what we observe. If m is equal to 1, we get that cosine of cosine inverse of z. So let's have a look. We get here cosine of times 1. So this is cosine of the cosine inverse of z is equal to what? What is this? Well, cosine of inverse cosine is simply equal to z. That means that the Chebyshev polynomial of the first order, it is z. In fact, this is of the 0th order, so we can say that this is z to the power 0, which is definitely equal to 0. Now here we get, for Chebyshev polynomial of the first order, this is equal to z to the power 1. If m is equal to 2, we can continue again and again. If m is equal to 2, we get the following. We get, let me write this here. We get cosine 2, and let's have a look. What is cosine inverse z? Cosine inverse z is equal to alpha. So we can write here cosine 2 alpha, okay? So what we are doing here, we're just trying to insert m equal to 2 on this expression, okay? And we know also that cosine inverse z is simply equal to alpha, okay? So we are writing this one carefully. Then we get that cosine 2 alpha is equal to what? Now we know that cosine 2 alpha, it is equal to cosine square alpha plus 1. So let's see if we have this here. Cosine 2 alpha, this is 2 cosine square, sorry, 2 cosine square minus 1, yes. This is equal to or is it wrong? Wait a second. So it's plus 1 or something. So then this polynomial, if we write this polynomial in terms of z, what we get is this polynomial. It's the first order, the 0th order, it was 1. The first order, it is z. We found this. The second order is 2z squared minus 1, and so on, and so on. So this is how we can use, and it is really interesting. I remember when I was a student, I found this one very beautiful definition, because imagine for a moment, if you are trying to find the Chebyshev polynomial of the 5th order, you have to substitute here 5, and you will have to describe cosine 5 alpha as a function of cosine alpha, okay? Anyway, so let's go back. This is how the Chebyshev polynomials of different orders can be described as a function of the fundamental frequencies. Again, what is the frequency here? This is 9 omega, okay, when m is equal to 9. If this is 9 omega, we are describing this high frequency as a function of the fundamental frequency to the power 9 times 256 minus the fundamental frequency to the power 7 times this constant plus z to fundamental frequency to the power 5 times this coefficient, and so on. So let's move ahead. And here we can observe what are all the Chebyshev polynomials of all of these orders. So Chebyshev polynomial of zeroth order, let's have a look. What was zeroth order Chebyshev polynomial? It was 1, right? So Chebyshev polynomial, it is 1, or z equal to 0, z to the power 0. So this is, you can observe this is 1. So this is this constant value, which is this dark line. This is Chebyshev polynomial of zeroth order. Then the Chebyshev polynomial of the first order, it is this line. Actually, in fact, you can read it like this. Maybe I should, yeah. So this line, which this is actually Chebyshev polynomial of the first order. Then we get this relationship, which shows that this is somehow the quadratic expression. So this one, this is kind of an equation y is equal to x squared. Është katror Chebyshev polynomial I gradës tret është y fuqi të tret e kështu me radhë. So that's how it increases. So here we see the Chebyshev polynomials, and if you notice carefully, we are going to see a little later that the amplitudes of the waves in a specific antenna when we have several arrays. So now this is really something beautiful, which I'm warning you in a good sense, that this is what you're going to expect. You have, let's say, you have 10 antennas or 10 linear antennas. We put them into an array. We construct a system which is now larger. And this system which is now larger, you might remember that the length scale, it was described as I forget how we did it. This was something like n times lambda plus d some. So there is a relationship between the length scale being n lambda plus d, more or less is something like this. But then if n was equal to 10, that means that the wave distribution is going to look like a Chebyshev polynomial of the 9th order. But then what we have to do is that we have to add up all of these Chebyshev polynomials, and we have to look at the plotting of this polynomial as a function of z. Okay. Now this as a function of z, this will be this z will be a function of beta d, etc. So you can have a look afterwards when we go to a graph that looks like this. We are kind of reminding each other what that one is about. And another important thing that we should notice is that the Chebyshev polynomials, they are defined only when z is smaller or larger than 1. And let's have a look here. Why is this the case? Because if we are describing the Chebyshev polynomial as a function of z, we see that z is equal to the cosine of something. And cosine, those are the real limits of this z. But when we are going to observe different antennas, we're going to see that in these graphs, we're going to sometimes analyze how this amplitude is increasing very fast, even beyond z larger or equal to 1. But let's talk about this one when we come to those examples. Now, when it comes to trying to design an antenna using the dot Chebyshev polynomials, or the antenna, it can be called dot Chebyshev. Let's see actually how we can design it, and let's assume that we're going to have a broadside antenna. For a broadside antenna, because we know that the phase difference between any two antenna components should be equal to 0. You remember that at the beginning of this session, we kind of proved that the beta, it was equal to 0 in case, because if you remember, I don't know to go back, but there was something like this. Cosine KD, I might forget, but you may correct me. KD cosine theta plus beta, or sometimes we have minus here, but I believe this is plus, which means that for a broadside antenna, if you want to look for the maximum highest intensity, broadside is that this is theta is pi over 2, cosine pi over 2 is equal to 0. That means that this is 0 plus beta. Cosine beta, we want maximum distribution. Cosine beta should be equal to 1. But if this is, so this is cosine beta. If cosine beta is equal to 1, that means that the beta will be equal to 0, okay? So the phase difference between any two subsequent antenna components, this is what it should be. We can always derive this one from the what we learned in the previous session, and then we have to specify the number of elements. If you want to make a broadside antenna using Chebyshev coefficients, we are going to select, let's say, n elements. From these n elements, we can determine whether, well, we have to figure out whether it's an even number or an odd number, because there is a fundamental difference between being odd and even, the same way that we saw for the coefficients in the binomial distribution. So the first important element is the number of elements. That's good, n. And then the second essential element is something we talked about the first part of today's session, where we need to determine what is the side lobe level, which is the voltage ratio between the major lobe and the minor lobe. So we want to see how much smaller will be the next subsequent minor lobe with respect to the major one. So that means that often, if we want to design an antenna, we have to know what is n and what is the voltage ratio between the major and the secondary lobe. And then if we are given these two components, we have to determine the amplitude coefficients and the D, which is the distance between any two components. Now, array design, again, if you want to design a broadside Chebyshev array, it can have several elements. The side lobes have a ratio which is defined as R0 unit in decibel. And then the general expression for the array factors, that's how they look like, which are these expressions around here. And first we start by trying to select an appropriate array factor, which can be given by 6.61. Okay, so we are in the previous slide actually, apparently 6.61. Maybe we can move a little faster. So these coefficients that we're looking for, this is how the array factors are going to look like. Yeah. So this will be described as a function of the cosine of some high harmonic. What is this? This is Chebyshev polynomials. Okay. Then in fact, this array factors, actually, here they are. So I was looking for the equation, but that's actually what these array factors are. Only that we have to kind of remind that the u that we observe here is equal to pi d divided by lambda times cosine theta. Let's not forget that the equations which describes the array factors, most of the time they had to deal something like this. It was something like cosine kd cosine theta minus, what was this other term? I forget. Minus beta, okay. So with terms that look like this, but now this u is something like pi d divided by lambda, and this is in fact, this is the kd. This factor, it is the kd, because lambda, it is inverse k. That's good. So the AF factors is going to look like this, and then we have to expand the array factor. And when we do the expansion of the array factor, we have to, so let's say we have n, okay, so let's say we have to describe or expand every term of cosine mu, which is the cosine of integer value times some fundamental frequency. We have to expand this in terms of cosine u, okay? Then afterwards, we have to determine a specific point, z equal to 0, or such that the Chebyshev polynomial that we're going to deal with will be evaluated at some z0. And now this Chebyshev value will give the voltage ratio, but we can make this clear when we start a specific example. Then the m order of the Chebyshev polynomial is always less than, okay, I think we talked about this one before. The order m of the Chebyshev polynomial is always one less than the total number of elements. We know this by now. The design procedure requires that the Chebyshev polynomial where in the, so this is how the z is defined, and z1 is the nearest null to z equal plus 1. Okay, so when we come to an example, we'll try to make this a little more clear. Now, once we get this expansion of the Chebyshev polynomial, and now let's try to remind again what was the expansion. Describe cosinusin, duke përshkruajmë cosinusin e 9 omegave si funksion I cosinus të omegave. So 9 omega is the frequency, omega is the fundamental frequency. And then after we do this expansion, we're going to observe several terms, and then we have to equal several terms. Now this really can look like a little challenging, but when we go to the example, it will be clear. Okay, but let's move again. And by the way, we can start an example, but before we start this example, we can give a very short break. Okay. Do you have any question?